epoxides undergo lots of interesting chemistry. That's again how you make epoxy resins. The epoxide undergoes ring opening with a nucleophile. Gee, you know all this now. And that generates this polymer that's very strong. We're going to do ozonolysis. Ozonolysis can be done two ways. Really the way we're going to talk about is the first one here, where we do ozone followed by dissolving metal workup. Dissolving metal workup, you literally take a little bit of zinc in acid, it bubbles. And as it bubbles, it generates hydrogen gas. And the hydrogen gas is what actually cleaves the intermediate ozonide. It's a nice reaction. Ozone, as we know, is up in the upper atmosphere, very important. It absorbs UV radiation. If you breathe ozone, it's bad for you. And the reason is it reacts with double bonds. We know we have lots of them. And in fact, cleaves them. Here we're going to make aldehydes and ketones. If we did an oxidative workup, we would get carboxylic acids and ketones. Finally, brutal reaction here. Potassium permanganate and acid. Now we've seen that permanganate in base gives us 1,2-diols. Permanganate in acid is very strong oxidizing agent. It splits your double bond. We'll wind up with carboxylic acids, ketones, and CO2. All right, so let's start up here with epoxides. This is an example of an organic peracid. Peracid is just like a carboxylic acid, except it has one more OH group, one more oxygen. This is a very reactive oxygen here, and it can split off in a fairly concerted reaction. You don't need to know this mechanism, but it's amazing to watch all these arrows at once. Oops. Here they come. So all of this stuff happens at the same time. One magic little reaction. This oxygen, bottom line, winds up being donated to the pi system, and we wind up with the epoxide. You don't need to be able to draw these little arrows, but it's nice to know that they're there. The other product here is simply a carboxylic acid. Problems for this would look something like these.
No movie?
No movie. This is our peracid. Again, way too many oxygens. That's how you know it's a peracid. And all you're going to do is take the oxygen from the peracid, going to add it across the alkene, and you will make an epoxide. Here, we have a double bond in a ring. Remember, the geometry of the epoxide requires that both bonds be on the same face of the ring. Therefore, when you do this reaction, you wind up with this as a structure. But remember, as I've drawn this, our ethyl group is coming out towards us, and this group is going back. Both of these bonds are on the same side of the molecule. And finally, this guy. Once again, the chemistry is simple. We're just going to add our oxygen across our alkene, and it's going to look like that. Toughest part of this is being able to imagine these strange structures. But if you can overcome that, it's not so difficult. I said that the epoxide ring was reactive. Remember I said that we could take potassium permanganate and an alkene, and we could make a cis 1,2 diol, right? What if you wanted to make a trans 1,2 diol? What would you do? Well, it turns out that epoxides react with aqueous acid to form trans 1,2 diols. So, if you go back to here, if you wanted to make a trans 1,2 diol on this, you would first make the epoxide, and secondly, dump it into acid. Doing this in the form of a problem, here we have cyclohexene. Here we have a peracid. That's step 1. Step 2, we dump it into aqueous acid. That's going to open our epoxide, and we will get a trans 1,2 diol. I've drawn them both equatorial. Remember, they initially start off both axial, but they are trans. That's the important thing. If instead we wanted a cis 1,2 diol, we would simply take permanganate and base, and we'd wind up with cis stereochemistry for our hydroxyl groups. So that's kind of neat. Gives us a good way to make both cis and trans 1,2 diols. The next reaction is also kind of neat. This, we are simply splitting an alkene with ozone. When we take an alkene and it reacts with ozone, it forms an ozonide. Basically, these are the 3 atoms of ozone, O3, and all they've done is add to our double bond, just like everything else. Adds to the nice big pi system. The ozonide will break down spontaneously, but it works better if you throw in a little bit of zinc in aqueous acid. As it dissolves, you get hydrogen gas bubbling off, and you wind up, in this case, with 2 aldehydes. Now, how do you predict what you're going to get here? All you do is go back to your starting alkene. Draw a dotted line through it. Each of the alkene carbons is going to be a carbonyl. That's all you have to do. So here we have benzene ring, carbonyl, and here we have CH2, carbonyl.
You're going to show us?
So let's do some work here. This is propene. If we take propene, ozonides, followed by a dissolving metal, what we're going to do is simply split along our carbon-carbon double bond. When we do that, both of these carbons wind up as carbonyls. This has a hydrogen and a methyl group, and this has 2 hydrogens. Our next guy here, we're going to split. This carbon has 2 methyl groups, so it'll be a carbonyl with 2 methyls. That's a ketone. This one has a hydrogen and an ethyl group. The pair looks like this. Now it gets fun. We're going to split here, aren't we? This is going to be a ketone. Ethyl group on one side, and then the rest of this ring on the other. This carbon is still going to be attached. It has a hydrogen in the rest of the ring, and it'll be an aldehyde. It'll look something like that. Again, this is where our double bond used to be. Ketone and an aldehyde. Same sort of thing here. Both of these have a hydrogen attached, so it's going to be a dialdehyde with 1, 2, 3 carbons in between. Now that's a simple concept. Just remember, ozone splits. If you do zinc and acid as your second step, you wind up with ketones and aldehydes. Our last reaction here is our brutal reaction. Potassium permanganate and acid. This is what we use for cleaning solution. So when you really make a mess in your round bottom flask, it's full of tar and stuff like that, what you do is you take sulfuric acid, potassium permanganate. You have to be careful because if you add it all together at once, it explodes. I actually proved that to myself once in high school. It was, well, yes, it was in the little prep room, and I was making cleaning solution. I dumped it all together. It started smoking purple. I said, something doesn't look right. And I had sense enough to walk out. Just as I closed the door, it exploded. I said, oh shit. Open the door. The walls are all coated with this stuff. I said, oh my gosh, I'm going to clean it up. I grabbed paper towel, wiped it, and as I did, it's such an oxidizing mixture, the paper towel burst into flames. So instead, I took the hose that we have, like attached to the faucets, and sat there and just hosed down all the walls with the door closed so the teacher wouldn't see. So you have to do it very gently, but it's a very powerful oxidizing mixture. If you have hydrogens, this is going to remove the hydrogens and replace them with oxygens. So if you have a CH2 on one end, this carbon winds up as CO2. If you have hydrogen simply attached, it winds up as a carboxylic acid. So our central carbons become carbonyls, hydrogens go to OHs. If you have a tetrasubstituted here, you would simply cleave it into 2 ketones. Very brutal reaction, not real useful synthetically. Let's just do a couple quick examples. Our first one here, just to show finesse. We have ozone, followed by dissolving metal. That's a very gentle, very specific way to split a double bond. We're going to cleave off this as an aldehyde. This is going to stay as a ketone. That's the bond we're breaking. This is formaldehyde, and here's our ketone. If we take this guy and we use acidic permanganate, Once again, we're going to cleave this double bond. When we do it, this is going to be a ketone, but because this has a hydrogen, it will be a carboxylic acid. Any questions? Well, let's just mix some of these up a little bit and pretend this was test A. Very quickly, jot down products for each of these reactions. Now I think you can see how you can write an organic test that could be really interesting. In chapter 9, which we'll do next week, we will take all of these plus alkyne reactions and combine them into what's known as synthesis, where we work backwards, do our reactions backwards. That's the real fun of it. We've done this one. We're simply adding HCl to an alkene. That's trivial. We know. What do we know about this? This is Markovnikov addition. It's going to be a carbocation intermediate. All we're going to do here is simply add a halogen to one of the alkene carbons. Our next one, this is HBr peroxide. We recognize this as a radical reaction. If we have stereochemistry to worry about, this is going to give us anti-Markovnikov addition, which means our bromine is going to be on the carbon that would form the least stable carbocation. That's this guy. Therefore, this is our structure. The addition of bromine to an alkene. We know that that occurs through an intermediate bromonium ion, no rearrangement, and the bromines are trans to each other. I've drawn them both equatorial here, but remember, the important thing is to show that they are trans. The addition of HCl, just like up top, this is Markovnikov addition, carbocation intermediate. We can get rearrangement, chlorine on the carbon that gives the most stable carbocation. Any questions? An alkene plus HOBr. We know that this goes with an intermediate bromonium ion. Instead of Br minus attacking, however, the hydroxyl group attacks. You need to show that these are trans relative to each other. Hydroxyl up, bromine down. Hydration. Kind of a powerful, non-specific reaction. We're going to make a carbocation. The carbocation is going to add water, or OH minus if you want, to the most stable carbocation. We will get rearrangement. Here we're simply going to add to our secondary carbon to give isopropyl alcohol. A more civilized way to do Markovnikov addition. Remember, it's an intermediate mercurinium ion. We are going to wind up with water attacking the most stable carbocation. Again, Markovnikov, but no rearrangement. Once again, HOBr. This is going to add to our alkene, intermediate bromonium ion. Hydroxyl group is bonded to the carbon that gives the most stable carbocation. And that's going to be our tertiary center. Remember, this is a trans addition. We had all single bonds here, so we don't have to show it. All right. I also put a worksheet on the blackboard site. Does everyone have it?
Yes, yes, yes.
You guys? Three of you. Yeah, one. You guys are okay? All right. Do a couple process. These are simply the same reaction over and over and over again, 7 or 8 times. And it just gives you experience in looking at reaction conditions and then doing the chemistry. Here we are adding halogen. Usually you do this in something like carbon tet. It's actually used that way as a test for a double bond. So if you have a molecule and you think it's an alkene, it's an unknown. What you do is you take bromine and carbon tet, or iodine and carbon tet. They'll either be, well, bromine will be dark brown, iodine will be purple, and you just add tiny drops of it. If it's an alkene, as soon as it hits the brown or purple color, disappears. It's a very fast reaction, very good. We remember that it goes with an intermediate bromonium ion, and we wind up with a 1,2 dibromide with trans stereochemistry. Therefore, we need to show our bromines are trans. Chlorine, same thing. We're going to add a chlorine to each carbon. Don't have to worry about stereochemistry, obviously. Here we have to show the stereochemistry. We have to show that they are in fact trans to each other. Here I've used wedgies. Again, just to show bromine up, bromine down. We're going to add a bromine to each of these carbons, and it'll look like that. The next set.
I'll go back on this one.
This is recording, I think.
Oh, okay, okay.
So,
Thanks, sir.
and anyway, you know, it's just, I'm doing these fast because I don't want you to be able to write them down.
You're not gonna have the answer, they're not, you gotta put the
Unless
answers
you-
on. You gotta have the answer so we can look at it.
Well, that's why it's being recorded.
Good.
All right, here we have styrene. We've all heard of polystyrene. That's styrene. And we're simply going to add chlorine. All we do here is add to each of the sp² carbons. The benzene ring does not react. That's one of the peculiar things about benzene that drove people nuts for years. So we're simply going to add chlorine here and here and get that as our product. Once again, we're adding bromine to this carbon and this carbon. Don't have to worry with stereochemistry. And one more time. Going to add to our exocyclic double bond. One bromine there, one here, and that's our product. Test 2. Here we have a large ring at 6, 7, 8, 9, 10 carbons. Double bonded it. We're going to add chlorine. What you need to be able to show here is the stereochemistry. Remember, they are going to be trans to each other. I've shown it just with Reggie's. That works fine.
Because of size, right?
Yep. And finally, one more time, chlorine and carbon tet, double bond, trans addition. Any questions? Addition of HOBr. What do we know about this reaction? We know it has an intermediate bromonium ion instead of bromide ion attacking. However, here we have OH minus that's going to be our nucleophile. The regiochemistry is such that the OH is bonded to the most stable carbocation. So we look at this. These are both secondary centers. All we have to do is show trans stereochemistry. With our next one, we have a secondary center and a primary. Remember, the most stable carbocation would be on our secondary. So that's where the OH group goes. This one, we not only have to worry about Markovnikov, but we have to show stereochemistry. The OH is going to go to our tertiary carbon, bromine here, and they must be trans to each other. Finally, HOBr, hydroxyl group will go to our tertiary carbon, bromine on our secondary carbon. Don't have to show stereochemistry.
Dr. Young, just so we're clear, the only time when you put it not on the carbo, on the tertiary, is when, what type of a reaction?
Well, that's anti-Markovnikov regiochemistry. We have two examples of anti-Markovnikov. Radical addition of bromine, or HBr, and BH3 followed by oxidation, which gives us an anti-Markovnikov alcohol.
NH3 you said?
No. Barely remember it. All right, quickly jot down these. We're adding HOCl. Hydroxyl group will bond to the carbon that would give the most stable carbocation. That will be the benzyl. Therefore, the product would look like that. Once again, HOBr, we will add the hydroxyl group to the tertiary carbon, bromine to our primary carbon. Tertiary carbon, primary carbon, hydroxyl group goes here, bromine goes there. See how simple all this is? Two more. Our 10-member ring again, HOCl. All you have to do here is show we have trans stereochemistry. Markovnikov selection, hydroxyl group here, trans addition, and it looks like that. A nicely civilized way to make Markovnikov alcohols. involves reaction with mercuric acetate followed by more hydride. We know that this involves a mercurinium ion, and because of that we don't get rearrangement. What we do get Markovnikov regiochemistry. Here we don't have to worry about it. We're simply going to put the hydroxyl group on one of the sp squared carbons. Here's our secondary carbon, here's our primary. Hydroxyl group will go to the secondary because that's the most stable carbocation. Our mercurinium ion will form between the two carbons of the alkene. Hydroxyl group will go to the carbon that will give the most stable carbocation. Once again, tertiary carbon, secondary carbon, hydroxyl group here. Our friend styrene again. Our most stable carbocation will be the benzyl center. That's where the hydroxyl group will go. Tertiary carbon, primary carbon, hydroxyl group on the tertiary carbon. Tertiary carbon, primary carbon, hydroxyl group here. And the last two. Our 10-member ring. All we're going to do is add a hydroxyl group to one of these carbons. Doesn't matter which one. This is our Markovnikov carbon, our tertiary center. Hydroxyl group will go there. Remember, you don't have to worry about rearrangements. Now here we're going to have to think about Markovnikov regiochemistry and the fact that BH3 is going to form this alcohol with syn addition. That means the hydrogen and the OH will be on the same side. Now you really can't tell in a structure like this. We are going to simply add our boron, do our transfer, we wind up with a simple alcohol. With this one, however, we have a secondary carbon and a primary. Remember, this is anti-Markovnikov. Therefore, the hydroxyl group goes to the wrong carbon. This would be the most stable carbocation, so the hydroxyl group winds up here. Once again, we have a tertiary center and we have a secondary. The anti-Markovnikov alcohol will have the OH on the secondary center. I've shown the OH and the hydrogen on the same side. This is the anti-Markovnikov carbon. That's where the OH group winds up. Our next set of three. Well, there they are. Well, I guess that's the product. But we're starting it with styrene. This would be our most stable carbocation, that is the benzyl one. That means the OH group will add out here to the primary carbon, and this is our product. Tertiary center, primary center, hydroxyl group on the primary carbon. Tertiary center, primary center, hydroxyl group on the primary carbon. The last two in our set. Our 10-membered alkene. Both of these are secondary carbons, it doesn't matter. We simply need to add the hydroxyl group. Here we have a tertiary center, a secondary center, anti-Markovnikov regiochemistry, the OH on the secondary carbon. We also have to show that the hydrogen and the OH are cis to each other. Let's make some epoxides, not epoxides, cyclopropanes, I mean. Difficult thing here is imagining these bizarre structures. We know that chloroform and KOH is going to give us dichlorocarbene. So our cyclopropane carbon will have two chlorines attached, and it'll simply bridge the two sp squared carbons. You don't have to show stereochemistry here, but I did. Diiodomethane, zinc, copper, ether. We know that this is going to give us CH2, carbene itself. It's simply going to add to our double bond here and make this cyclopropane. Dichlorocarbene again. Going to add across here, wind up with two chlorines. There's our ethyl group. I left off the chlorines, oops. But you could write them in. Once again, dichlorocarbene, make our cyclopropane here, and this time I put the chlorines in there.
The one above it, where does it go?
The chlorines go on the cyclopropane carbon. Well, I think I did the same thing here. So we're going to add to our alkene here. We will make a dichlorocarbene. Again, I forgot to put the chlorines on. I just did these slides this morning, so. Diiodomethane. This is going to give us carbene itself. Simply going to form an a cyclopropane between these two carbons. Once again, we're going to stick our carbon onto this double bond. Make sure that you realize that this is the same structure as if I had just drawn it sticking out to the side. Dichlorocarbene, going to add here. Again, you need to stick 2 chlorines out here, sorry. And finally, this is going to be carbene itself. Simply going to add across here. And that's our structure. Now the next one is very, very simple. This is hydrogenation. We're taking double bonds and making single bonds out of them. Hydrogen gas, platinum on charcoal, and ethanol. All we're going to do is convert this into a single bond. Same thing here. We're getting rid of our double bond. Now, with this one, we need to think a little bit about stereochemistry. Remember, the hydrogens come on from the same side. Therefore, when we reduce this double bond, we must show that our methyl groups are going to be cis, because our hydrogens must be on the same side. Hydrogen and platinum does not reduce a carbonyl easily. It can if you really beat on it. We'll see that in chapter 17. But all we're going to do is reduce our double bond here and make this simple ketone. If we take styrene and we reduce it, once again the benzene ring is very resistant to reduction. You can, but it's very resistant. Therefore, the only thing it reduces under normal conditions anyway is going to be our double bond, and we get ethyl benzene. Our carbon-nitrogen triple bond can actually be reduced to a primary amine, but that happens very slowly. So if you do it under gentle conditions, only thing it's reduced is our double bond, and we wind up with this nitride. If we reduce this guy, this just becomes a methyl group, doesn't it? The last two. Here I've taken my 10-member ring and I have moved my double bond to the middle. Now, why in the world would I do that? So you have the opportunity to show that in fact a reduction occurs with the hydrogens on the same side. Therefore, you somehow have to show the stereochemistry here. That would work. Same thing with this one. We're going to add hydrogen on the same side, leaving the two methyl groups cis. And finally, oxidations. Osmium tetroxide. Remember, that's going to be a 1,2-diol. The hydroxyl groups are going to be cis. We'll have a hydroxyl group on each carbon. Again, cis stereochemistry. Ozonolysis followed by reductive workup. We are simply going to split our double bond. Each of these carbons will become a carbonyl. That means we wind up with this aldehyde from this half and formaldehyde from this half. Permanganate and acid. We are also going to split our double bond, aren't we? This has 2 carbons, so it will be a ketone. This has a hydrogen, so this is going to wind up a carboxylic acid. In between the two, we have 1, 2, 3, 4 CH2 groups. Once again, permanganate and acid, very powerful. This carbon has 2 hydrogens. It will be CO2. This one has 1 hydrogen. It will be a carboxylic acid. The next 3. Osmium tetroxide again. We are going to make a 1,2-diol, so a hydroxyl group on both carbons.
Splitting, right? Again.
Not
We're
splitting.
Oh, you're not splitting.
No, just like permanganate, just a 1,2-diol. Now this, with this third step, would actually split the 1,2-diol. We're going to pretend because we haven't done that yet. That will be in chapter 17. But osmium tetroxide is simply going to convert our double bond into a cis 1,2-diol. Here we have ozonolysis. All we're doing is splitting our double bond. This is going to be formaldehyde. This guy will be a ketone.
So now you're splitting it. Why do you not split on some cases and some cases you do?
That's ozone.
Okay, so ozone, got it. Where is it?
Not osmium, ozone.
Hold on a second, let me write this down.
And our last 2. And then we can all go away and be shell-shocked. Acidic permanganate. Each of these sp² carbons has a hydrogen. So each of those carbons will be a carboxylic acid. And finally, osmium tetroxide, we're going to get a cis 1,2-diol. We have a ring, so we have to show stereochemistry. Hydroxyl groups on the same side. Now see, that's not so bad, is it? Not at all. Thank you. Thank you for saying that. All right, as soon as I work out the details of the lab, I will send you stuff, and we'll do something. I'm not sure what it is yet, but we'll do something on Thursday. Also, if you want to stay after lab, remember we can always do that. We can talk about reactions. If you want to work your sheets and you have any questions, perfect time.